This segment of Technical Forum is about, it's part 2 in a series of covering unintuitive electrical hazards. And this one is about magnetic induction. So briefly, some key terms. So this is a hot stick in red in this photo here, and then these are portable earths, the yellow cables with the metal clamps connected. And the portable earths are used in high voltage isolation to prevent dangerous voltages. And when a worker goes to connect the portable earths, they use a hot stick for that purpose. And the hot stick's important because it allows the worker to remain at a safe distance for that task. And it's fully insulated, which is important because there could be a voltage on the circuit conductor. Now, when the worker goes to apply the earths, they're expecting that there's no voltage on the circuit conductor, but sometimes there could still be a dangerous voltage. One reason why this could happen could be that the operator might have made a mistake in their isolation. And there are other reasons as well, which we're going to look at. And here's one scenario where a worker might need to apply some portable earths. So I'll just very briefly repeat the question from quiz 2 that we went through in part 1. So a linesman's about to connect a set of earths to an overhead line, and it's already earthed at the remote end, and there's a parallel transmission line next to it that's still in service. If he accidentally touches the line a moment before he applies the last earth, then he'll receive a shock. So the question is, which circuit elements best illustrate where the energy comes from? And the options that we had either lines are like a capacitor, and or the lines are like a transformer, and or the lines are like a battery, and or the linesman's like a Van de Graaff generator. And it was select one or more. So let's look at the theory for this. We've got a wire carrying a DC current. So what does the magnetic field look like? Yeah. Around it. Like okay. Okay, that's close enough. Yep, all good. And now we've got a single phase transformer. Now the secondary winding is in a bit of an odd spot, and you'll see why later. Where does the magnetic flux go? Yeah, in the core. Yeah. That's the magnetic flux. You can plot it like this. So the purple is the location of strongest flux density. So that's where most of the flux is. And for a thought experiment, we're going to replace the steel laminations in our transformer with timber. We now have a timber core transformer. And the timber is magnetically like air. So all it's doing is just holding the coils in place. And let's say that we want to know whether, given that we're applying an AC voltage across the primary winding, we want to know whether we still get a voltage across the secondary winding because we've replaced the core with timber. So what kind of invisible quantity do we need to think about to figure out whether we're still going to get a voltage on the secondary winding?
Flux path.
Flux path, okay. And specifically, it's whether the flux path goes through the secondary coil, right?
Yeah.
Yeah. So the magnetic flux through the secondary coil is the key thing here. Now that's a bit abstract, so we'll just explore this concept of magnetic flux a little bit. So we're going to use this loop of wire to explore the concept of magnetic flux through the loop. And we're going to look at the voltage across the loop as well. So this is the same loop again. We're looking at it side on in a uniform magnetic field. And you can think about flux as sort of how much of the magnetic field is passing through the loop. That's the very rough definition of it. But for a bit more precision, there's an analogy you can think of, which is a stream of water. So you can think of the magnetic field as like a stream of water, and imagine putting the loop of wire in the stream of water. And then the question is, how much what is the flow rate of the water through the loop? That's what the flux represents. Flux is analogous to the flow rate. So then you realize that the flow rate of the water through the loop depends on not just the speed of the water, which would be analogous to the field strength, but it also depends on the size of the loop, and it depends on the angle that you're holding the loop on, because the angle that you're holding the loop on might determine the flow rate of the water through the loop. Does that make sense? So if we rotate the loop, so it's on a bit of an angle like this, are we going to have more flux through the loop, or same, or less, or no flux through the loop? Less flux, yes. And you can think of that in terms of the water analogy. And in this case, same flux, more, less, no flux through the loop? No flux through the loop, Robbie? Same as if you're holding a loop of wire in a stream of water. In this case, on this angle, the water just goes past the loop. It doesn't go through the loop. Same with the magnetic flux. Now, there are limits to this analogy. If you put a leaf in a stream of water, the water's going to move it downstream. The magnetic field won't do that. Just in case there was any confusion. It is only an analogy, and analogies have limits. Now, I'll show you a bigger version of this plot in a moment, but what it's saying is that if the magnetic flux through the loop is changing over time, then that means you're going to get a voltage induced across the loop. And the bigger the loop is, the more flux you're going to get through the loop, and that means the bigger the voltage is going to be. So we'll need that later. So just a closer view of this plot. So on top, we've got the magnetic flux varying over time. So the flux is set up by an AC source in this case, and that induces a voltage across the loop, which is also going to be AC. And the voltage is actually equal to the rate of change of flux, but just in the opposite direction. There's an equation in the appendix if you're interested. So now we're back to our timber core transformer again. So we want to see whether a voltage is induced in the secondary winding. And so the next step is to look at the magnetic flux through the secondary winding, just as Mark was saying. This heat map represents technically the flux density. Now, just a nuance of the definitions, magnetic field strength and flux density here are equal because we have air and we have timber, which is magnetically the same as air. So we can use the terms interchangeably in this case. So the purple represents the strongest area of the magnetic field, and then the blue is the weakest area. And the arrows are an indication of the direction, though it is set up by an AC source. So I've marked in bold there some of the arrows for the magnetic field around the secondary winding. I've marked the axis of the winding with that dotted line. So that's this over here. So you can see these arrows and the axis of the coil. So the question is, when you're thinking about the loop again and the angle of the loop in the stream, are the magnetic field lines here adequately aligned with the axis of the coil to cause a net flux through the secondary coil? What do you think? Yeah, they are. They're less than 90 degrees away from the axis of the coil, so we do get a net flux through the secondary coil. And that means that we do get a voltage across the secondary coil. Not the same as you'd get with the transformer that had the steel laminations in the core, but still a voltage. Now, you should be wondering why the core of our transformer is made of timber. It'll make sense soon. So all good so far? So the question in quiz 2 was we needed to see where the shock energy comes from. So we can make a hypothesis for this. Let's say the shock energy is from a transformer effect between the two transmission lines. That was option B. The two transmission lines in parallel are like a transformer. Now the question is, how do we decide whether that's a plausible explanation for where the shock energy is coming from? So we can use our loop again. Now, to see whether the transformer effect caused the shock, first of all, we need to identify a loop that the flux is passing through. And then, once we've identified a loop, we need to figure out, is there actually a net flux passing through it? And if there is, then it should be changing over time because it'll be due to an AC source. So that's how we decide whether the transformer effect is causing the shock in this case. Make sense? Yeah. So I'll zoom in on this in a moment, but this is our scenario for quiz 2. So on the left, we have the elevated work platform and the workers standing in the bucket. And on the right, far in the distance, many kilometres away, we have a set of portable earths that are earthing the circuit conductors to the foot of the tower. And it turns out that the isolated circuit conductors and then the portable earths off in the distance, and the earth return path through the soil, and then the path through the elevated work platform, which is bonded to earth through the foot of the tower, and the worker, that all forms a loop. There's just an open point in the loop from the worker's head up to the circuit conductors above them. So there's a close-up. You can see that's the worker there in the bucket truck. Portable earths, they're not connected yet. And then the elevated work platform, it's bonded to the foot of the tower. So in yellow here, the yellow represents our loop. Just like the loop that we looked at earlier, this is the loop where we want to see whether there's a magnetic flux passing through it, because the magnetic flux would create a voltage. And that would be the voltage that presents a hazard to the worker. So here the crosses represent a magnetic field going into the screen. So that's the direction that we're interested in for the magnetic field. We want to know whether there is a magnetic field like that. And so to answer that, we need to look at the line from a cross section. So again, just like in part 1, we've got the towers far off in the distance, and then we've taken a cross-sectional cut of the conductors, simplifying them as just one conductor per phase, and we can model this. So there's our magnetic field. The colour represents the magnetic field strength, and then the arrows are an indication of the direction. So on the left, the energised transmission line, which is in service, that is creating a magnetic field, and then on the right, the isolated transmission line is in the magnetic field set up by the in-service line. So we can choose one of these conductors here, put a box around it. So let's say that's the red phase conductor on the isolated line. And our loop that we looked at a moment ago that we marked in yellow, now from this different angle, the loop is from that conductor down to the ground, the earth return path through the soil. So we want to know whether there's a net magnetic flux passing through that loop. So we can figure that out from these field vectors, the arrows. So now I've drawn a line down from this conductor down to the ground, and most of these magnetic field vectors are pointing to the right through the dotted line, right? Some of them are pointing the other way, but turns out if you add it all up, there is a net magnetic flux through our loop. So here's our loop again from a different angle. And you notice that the portable earths are quite far away from the worker. So in practice, it could be many kilometres. And because the earths are far away from the worker, that means that the area of our loop is actually very large. And if you have a large area in the loop, that means you have a large amount of flux passing through the loop. And so you have a large voltage. And that voltage is going to appear between the worker and the isolated conductor above the worker's head. So this is a schematic of what happens when the worker accidentally contacts the line. So the worker accidentally contacts the line, he closes our loop. Our loop has magnetic flux passing through it, varying at 50 hertz. And so I've represented this schematically here, where on the top we have our energised line with source and a load, and there's a load current flowing through it. and that's the inductance of the energized line. Now we're just simplifying this as just one conductor per line, so consider just the nearest conductor on each line. And then the nearest conductor on the isolated line, the worker accidentally touches it. The worker is represented by this resistor. Then there's the inductance, and then there are portable earths at the other end of the line. And because of the mutual inductance that couples these two inductances of the lines, there's an induced current, and that's flowing through the worker. So that's where the shock energy comes from. And so these two lines, they are like an air cored transformer. That's what the mutual inductance means. And so you can think of it like a transformer, except that with a transformer, you connect the primary winding in shunt to the source. Whereas here, we've got a series connected primary winding. So it's a transformer, but it's, in a sense, it's connected up the wrong way. So we can look at this analogy based on our plots. So on the left, we have our timber cord transformer. Now, the reason why I've got timber there is because timber is magnetically the same as air. All it's doing is just holding the coils in place. And so that's why it's analogous to our transmission lines on the rightmost image, because those form an air cord transformer. So we can look at the primary winding of our timber cord transformer. It's oriented around the vertical axis. If we choose two of the three conductors on the in-service transmission line, it's the same thing, oriented around the vertical axis. The main difference is just on the transformer, you've got conductors looped around many times. Whereas on the transmission line, they're not looped around many times, but they extend far into the distance. So in both cases, the conductors are long, and because they're long, they can produce a lot of magnetic flux. And likewise, the secondary winding on our timber cord transformer are oriented around the horizontal axis. That's like the loop that we looked at for our transmission line. So we look at one of the isolated conductors and the loop through the earth return path that I've marked on the right here, and also oriented around the horizontal axis. So those are analogous. So what we find is that the transmission lines, the two of them in parallel, they form an air cord transformer. Now, okay, if you're following so far, I can slow down if you like. Now it's just some nuances of this. Now there's some limits to this analogy. With a transformer, you expect that the voltage on the secondary winding it depends on the voltage that you energize the primary winding at. It's not quite the same here because in this case, the voltage that you get induced on the isolated line doesn't actually directly depend on the voltage of the energized line, this transformer effect. So this can occur at a range of voltages. So that's the limits of the analogy, transformer analogy. And so that means that the transformer effect is a source of shock current in the quiz 2 scenario. So that means that option B is correct. And the transmission lines are like a transformer. But counterintuitively, there is another source of energy as well. So for that, we need to do a very quick recap of part 1, just very briefly, because we covered this in detail in part 1. So in part 1, we looked at the quiz 1 scenario. The worker touches the line after they've removed the earths. So at that point, there are no earths on the line. And at that point, the shock comes from the capacitor effect. So we modeled it like this, with a capacitive voltage divider from the live line to the isolated line. And then there's a charging current flowing. And if the worker touches the line, then the worker, as this resistor here, has a shock current that flows through them. But it's different in the quiz 2 scenario. So in this case, I've added the portable earths. In quiz 2, the portable earths are at the remote end of the line, and they have a very low impedance. So most of the charging current of the line is going to flow through the portable earths in the quiz 2 scenario, even when the worker touches the line. Now, this raises the question of, well, if the resistance of the portable earths is so small, then why do you have any meaningful amount of current flowing through the worker? Why shouldn't it be a negligible current flowing through the worker from the capacitive effect? And the reason is that, you can see here, so this is the resistor representing the portable earths, and this resistor represents the footing impedance of the tower. So our portable earths, far off in the distance, they're connected from the circuit conductors down to the foot of one of the transmission towers. And the transmission tower, that's earthed to the general mass of Earth through some conductors under the ground. And that earthing to the general mass of Earth has an impedance. That tower footing impedance might be 20 or 30 ohms, whereas the impedance of the portable earths will be much, much less than 1 ohm. So this has a big impact here. So if the resistance of the worker is 1,000 ohms, consider the current splitting up between those two paths. Some of the current goes through the worker, some of the current goes through the portable earths. And it means the amount that goes through the worker can actually be significant. It can actually be enough to cause a fatality. So that's why it's critical one of the reasons why it's critical to earth everything at the work area, even if you've got remote earths at the other end of the line. And so this means that the shock current in the quiz 2 scenario is actually due to both effects, capacitor effect and the transformer effect. And the shock current in quiz 2 is due to the vector sum of the currents due to both of those effects, due to these models that I've shown on the right here, which we've looked at a moment ago. So there's a team of researchers, again, in America that have actually measured this effect in the field. So again, they looked at 2 transmission lines in parallel. One is in service at 115 kV, and the other one's isolated. And then they went a few kilometres away and they connected some portable earths and earthed it to the foot of the tower. And then a few kilometres away from the earth, they connected a resistor representing roughly the resistance of a person. And what they found was a bit over an amp flowed through the portable earths, and there was still 37 milliamps flowing through the resistor that represents a worker. So that 37 milliamps represents the shock current that would go through the worker if they touch the isolated line, which is earthed just a few kilometres away. And so to put that in perspective, an RCD will trip at 30 milliamps. This is more than 30 milliamps, so this is a potentially fatal shock. So this is what happens if the earths are not at the work site, not within line of sight.
Last question, please. How do you earth, so if you're earthing close, what do you earth it to? You don't earth it to the foot of the tower? If you earth it to the foot of the tower, you've still got 20 or 30 ohms, or are you just saying, like if there was a tower right next to you, like if you're working 20 metres from the tower, so you were earthing quite close, but you're still earthing to the foot, you've still got that 20, 30 ohms of resistance through the foot of the tower. So how does earthing closer negate the effect of the resistance of the footing to the tower?
You're also bonding the elevated work platform to the foot of the tower as well.
Ah.
Yeah. Okay, so the correct answer to quiz 2, where there's the set of earths at the remote end of the line, it's actually both A, this is due to the lines being like a capacitor, and then B, the lines are also like a transformer. Got both effects for the quiz 2 scenario. And just to clear up any confusion about the difference between those two scenarios, so in quiz 1, when the worker touched the line, there were no earths on the isolated line. In that case, it was just a capacitor effect. In quiz 2, when the worker touches the line, there are just the remote earths a few kilometres away. And in that case, we've got both the capacitor effect and the transformer effect are contributing to the shock current. So the term...
No, you go first.
Terms for what we're talking about here today. So simplest terms, capacitor effect and transformer effect. Now, alternate terms that you might see, the capacitor effect, you could also call it electric field induction, or the other term you might see is electrostatic induction. And then for the transformer effect, a more precise term you could also use is just magnetic field induction. You might also hear it called electromagnetic induction. Now, this is the most important part, practical implications of what we've been talking about. I think all of it's already come up in some questions, so we've discussed a lot of it. So again, same thing as Mark's question from part 1. When you remove the earths, the induced voltages appear instantly. These particular ones, the hazard will be there instantly as soon as you've removed the earths. And as we discussed, the earths are only effective at preventing these induced voltages if they're at the work site, within line of sight. And we're not just talking about hazards precautions against hazards which could develop, maybe rarely under special conditions, but in the scenarios that we looked at, the hazard is there continuously whenever the conductors are not earthed correctly at the work site. So with the scenarios that we were looking at, the hazard is there until the moment that you connect the local working earth, and the hazard appears instantly when you remove the earth. So when you're connecting or removing earths, stay at a safe distance using the hot stick. And if you need to access circuit conductors, just check that you've got earths on either side of the work site, and they need to be at the work area, not at a remote location. And then in part 3, we'll cover 2 more types of unintuitive electrical hazards, which appear in different kinds of scenarios and have different properties. So, and if you want to learn more about this, read more about it in detail, there's the IEEE paper, which is reference number 4. And then in the appendix, there's some equations if you're interested.